like. Okay, so yeah, it's my pleasure to introduce Honghao Gao from Michigan State University. And the title of his talk today is Augmentations, Fillings, and Clusters.
All right, thanks very much for the invitation. It's my great pleasure to have this opportunity to share some of my recent works that I'm really excited about. Let me begin the talk by this table here. Basically shows the main components that I'm going to talk about today. So I'm going to talk about some invariants for geometric objects in contact and symplectic topology. On the topological side, we're going to look at Lagrangian links and their exact Lagrangian fillings. And we're going to look at some invariants, which are algebraic constructions, associated to the some isomorphism classes. So for Lagrangian links, we're going to look at these augmentations, which are Flirt theoretical invariants, which I'm going to introduce later. And for the Lagrangian fillings, we're going to look at something called cluster algebras, which also defines an invariants for these fillings, which is one of the main results I'm going to present today. So let me begin with a few, from the very beginning. We look at Lagrangian links in the standard contact manifold that's R3, equipped with the one contact one form dz minus y dx. And a link, which is a union of circles inside R3 is the Lagrangian link if this one form vanishes on lambda. So here's an example of the right trifolio. So I plot here on the left the front projection, which is the projection of the nodes to the xz plane, and then the Lagrangian projection, which is the projection to the xy plane. And you can see this is also an example of the closure of a positive braid, where if you can see my anchor here, so I have two strands and then I braid them 3 times and then close it up to obtain a link. So one thing I want to point out is that in the front projection, the missing coordinate y can be determined by the slope of this inverse curve, because for alpha to vanish, y equals to dz over dx. So we don't need to, for the crossing, we don't need to specify which one is the over strand, which one is the under strand. They all have the same pattern. And you probably also notice that there's a similarity between these two diagrams, and that's just a manifestation of in-series solution, where you can obtain the Lagrangian projection from the front projection by smoothing out the left cusp, replace the right cusp by the small loop, and then keep all the crossings. So in this talk, I'm going to focus on the positive braid links. So that's so braid, a braid is some word of these arting generators satisfy these two relations. So a positive braid is a braid that I only allow positive powers of these generators. So because the front diagram has only one type of crossing, so by closing up a positive braid, I can obtain a front projection of a Lagrangian link in some canonical way. And then I can perform in-series solution and get a Lagrangian projection of this lambda beta. So for example, if my braid word is S1, S2 square, S1, S2, S1, which is this part of the braid. Okay, and then I can close it up and then perform in-series solution. This is what the Lagrangian projection look like. These crossings B and A are rep chords of degree 0 and 1, and I have some marked points here, which are used later to construct the Chekanov-Eliashberg DGA. Okay, so let me continue with what Lagrangian fillings are. So I can take the symplectization of my contact manifold, and then there's a canonical symplectic exact symplectic form, which is the differential of e to the power of t times alpha. And here's a picture depicts what I mean by exact Lagrangian filling. So filling means that I have a surface whose boundary is the Lagrangian link that we talked about before. Lagrangian means the omega vanishes. And I also want this to be oriented and has cylindrical end. And in particular, I want these Lagrangian fillings to be exact, meaning that this one form here has a potential. So it's exact when you restrict to the Lagrangian filling. So these fillings are somehow abstract to think about in the 4-dimensional manifolds. Let me briefly talk about some properties of exact Lagrangian fillings with a focus on compare its property in the smooth setting. So the first one I want to talk about is unknot filling. If you have in the smooth setting, you actually get a lot of unknot filling. The reason is that whenever you have a knotty two sphere embedded in S4, you can just chop off a disk. Then that gives you a smooth filling. And there are so many of them that we don't even have a classification. But in the exact Lagrangian setting, this is a theorem of Eliashberg and Pavlovich that the unknot filling is unique. So you can think about this unknot here as a plot, and then you start to you think about the filling as a movie that I shrink my knot to smaller and smaller, and eventually becomes a point, and then disappears. So that's a unique unknot filling as described by Eliashberg and Pavlovich. Another property is the genus of the filling. So in the smooth setting, you can only talk about the smallest genus of the filling because you can always perform the connect sum with a higher genus surface. But in the exact Lagrangian setting, this is a theorem by Shang that the Thurston Bannikin number equals to 2 times the genus of a filling minus 1, regardless which filling it is. So if you look at the left-hand side of the equation, this is the invariant of lambda. It doesn't depend on the filling. So which implies that if a Lagrangian link is fillable, and then all the fillings must have the same genus. So these two properties are important. The first property characterizes that exact Lagrangian fillings are sort of scarce, compared to smooth fillings, so that it's possible to enumerate, how many fillings are there. And the second property says, all the fillings have the same genus, and this hints on some of the algebraic constructions we will talk about later. So these are the properties of exact Lagrangian fillings. Let me explain how do we sort of see these exact Lagrangian fillings. There are surfaces in 4 manifolds satisfy a certain differential equation. In general, it's hard to describe them. There are several ways of thinking these surfaces explicitly. I'm going to talk about one construction by Ekholm-Honda-Kalman called decomposable Lagrangian fillings. So their basic idea is you can think about the Lagrangian filling as a movie of possibly singular Lagrangians. And what you're allowed in the movie is a finite list of moves. So first of all, you allow certain Lagrangian isotopies. And when you graph the isotopy, you got exact Lagrangian concordance. And then for the non-trivial moves, you can do the saddle cobordism, which is one handle attachment. So here on the left, you see a picture of a one handle plotted in the format of the front diagram of Lagrangian surface. It's a saddle that we're familiar with, but laying flat. If you think about this as a cobordism between the Lagrangian in the front and the Lagrangian in the back, so in the front, you see this pair of cusps. Okay, and in the back, you see these parallel strands. So you can sort of discretize this move, this cobordism by such a move that you collapse rep chord here and then make them two cusps. So in the Lagrangian projection, because there's a rep chord here that corresponds to this crossing, and then there's no rep chords here. That's just two parallel strands. So in the Lagrangian projection, the saddle cobordism is just resolved crossing like this. Okay, another one is the minimum cobordism. That's a zero handle corresponding to the unknot filling that we have talked about in the Eliashberg-Pavlovich theorem. That there's a unique filling for the unknot, and you just remove that. So any filling that's a concatenation of these three types of moves is called decomposable Lagrangian filling by Ekholm-Honda-Kalman. In this talk, we're going to look at a specific case of decomposable fillings in the realm of positive braid links. So let me introduce this cyclic rotation. That's a particular type of Lagrangian isotopy for positive braids. So at the braid level, the move just send the leftmost generator of your braid to the right. And why is that a Lagrangian isotopy? Is that if this is my braid, and what you can do is you can perform a Reiter-Meister 2 move by pulling the second left cusp upward. So you get to here, creating this pair of crossings here and here. Okay, and then you can perform another Reiter-Meister 2 move between, for this crossing and this crossing by pulling this lower cusp inside, and then you get to here. And the effect of these two moves is that this crossing goes from the bottom to the top, and then you repeat this on the right-hand side, and then you can rotate that to the right-hand side. So I draw this in the front projection because it's slightly easier to see the Reiter-Meister moves, but you can, this isotopy can be transferred to the Lagrangian projection as well. Okay. So we're going to look at these things called admissible fillings for positive braid Lagrangian link. And that's the composition of the saddle cobordism, which is, remove a crossing in the middle, or braid moves. This is a braid equivalence, and cyclic rotation and unknot filling. So let me show you one example. So this is the example I have seen at the very beginning. I have the Lagrangian projection of the right trifolio, and I have three crossings here. And remember the saddle cobordism in the Lagrangian projection is to smooth out by resolving a crossing and replace it by parallel strands. So if I resolve all three crossings, I got two parallel strands, and then I have a unknot inside, I have another unknot outside, and then I can fill up these two unknots, and that gives me an exact Lagrangian filling. The possibilities to create different Lagrangian fillings is I can resolve these crossings in different orders, and that potentially creates different exact Lagrangian fillings. So just takeaway is that there are three crossings. That's 6 permutations, and except for 2 of them are the same, we can get at least 5 exact Lagrangian fillings. So this is an example of producing exact Lagrangian fillings for positive braid links, where of course I only used the saddle cobordism and the unknot filling. So when you have more strands, you can start to perform braid moves, and you can also do the cyclic rotation. And combining those two moves, there's a vast amount of exact Lagrangian fillings that can be produced in this procedure. Okay. So now I have explained to you what are the geometric objects we're going to look at in the talk today. Let me continue with the algebraic constructions, the augmentation variety. So the augmentation variety, it's a two-step construction. We will start with the Lagrangian, and then we'll construct the Chekanov-Eliashberg DGA, and then this affine variety called the augmentation variety. So let me just walk through the definition very quickly. So the Chekanov-Eliashberg DGA is generated by the rep chords and formal variables. And in our previous diagrams, these rep chords are nothing but the crossings in the Lagrangian projection. And all these variables are assigned with a grading called Alexander index, which is some sort of version of the Masov grading. And the differentials are defined by counting immersed disks in the Lagrangian projection, or it's equivalently defined by counting pseudo-holomorphic curves in symplectization. For whatever this definition is, I'll show you an example slightly later. Once we have this DGA algebra in hand, we can define the augmentation, which is the DGA morphism from the Chekanov-Eliashberg DGA to this trivial DGA, where I put a ground field at degree 0 and set all the differentials to be 0. So what we want to do here in this talk is that we want to set this ground field to be an algebraically closed field of characteristic 2. I'll explain this slightly more later. Okay, and then you can look at the augmentation variety here. This is some sort of a moduli space. Let me say it's not the moduli space. It's a moduli space. Parameterized by how my rep chord, how my augmentation evaluates on the rep chords and the formal variables. Okay, I just collect the set of all augmentations. For each of them, that gives me a point inside k to the certain power. They correspond to the rep chord, and k star to a certain power. They correspond to the formal variables because formal variables are invertible. And in our setting, and this is true in general, that a generic Lagrangian has only finitely many rep chords. So this is a finite dimensional affine variety. Okay, so let me do an example. This is sort of abstract here. Same example, the right trefoil. Okay, so in this diagram, I have 5 crossings here. 3 of them come from the braid, which I call B, and 2 of them come from the resolved right cusp, which I call A. And the gradings for these generators are the formal variable, and these B's has degree 0, and all the A's has degree 1. And for the differential, it's defined by counting disks. Let's take A1 as an example. This is an immersed disk with a unique puncture at this quadrant of A1. So except for A1, where I started my disk, there are no other rep chords. So the counting gives me 1 here. And then this disk, okay, again, the boundaries on the Lagrangian projection. I have 2 quadrants, one at the A1, the other one at B1. So I start with A1, and then I turn once at B1, and no other turns, and this gives me the term B1 here. You can do a symmetric one that gives me B3, and then there's B1, B2, B3. So that's the differential of A1. You can check there are no other immersed disks. And the differential of A2 has 6 terms. Okay, slightly more complicated because when you go around this braid, when you have a right cusp, this small loop in the middle, the immersed disk can really go around this boundary along this knot. I'm not going to write down the whole thing, but it's more involved as you have more layers. At the end, we can compute the augmentation. It's the DJ morphism can be unwrapped by this equivalent definition that the composition of the differential and epsilon equals to 0. So if I apply epsilon to the left-hand side, the right-hand side has to be 0. So meaning if I set x to be epsilon b1, y to be epsilon b2, and z to be epsilon b3, this equation becomes 1 plus x plus z plus xyz equals to 0. The differential of A2 will involve a term including t. So, and that's uniquely determined in this case. That's epsilon t equals to -1. So, getting rid of this equation, this is the augmentation variety of the right trifolio given such a declaration of marked points. So that means every augmentation corresponding to a point in this variety and every point in this variety gives you an augmentation, defined by this relation. Okay, so what's important of such a variety is that this thing has a cluster structure on that, cluster K2 structure. This is some structure, algebraic structure first introduced by Fomin and Zelevinsky, and later on parallel track by Falk and Guntrov. So let me give you an ad hoc working definition for this. A cluster K2 structure on smooth affine variety is a collection of clusters or cluster seeds or just seeds, such that each cluster consists of 3 data. First, you want a tars chart, which is an open dense tars chart inside your variety. On each chart, you want some cluster variables. These are, coordinates on this tars chart. So they are tars coordinates, but it's stronger than an arbitrary set of tars coordinates. They have to come from global regular functions on the entire variety. And the restriction of these global regular functions to the tars chart become certain tars coordinates on the chart. And moreover, the cluster variables from different cluster charts are related by a quiver, which is also part of the data inside this cluster. And this is actually a very strong algebraic construction because we require the transition maps to be certain type of Laurent polynomials. And these polynomials are governed by the quiver mutation. So below this formula shows you an example of how the transition map look like. Just a single mutation. What happens is that when you mutate from one cluster chart to another one, you get new cluster variables. And this new cluster variable, which I label with prime, will have to look like this regarding all the old cluster variables, which doesn't have the prime. So when I move an to the right-hand side, you see this is a Laurent polynomial. So you can see that this is sort of put a lot of constraints between these clusters. And there's a combinatorial way of organizing these clusters. It's called an exchange exchange graph where you can just draw a graph, a connected graph where all the vertices are clusters and the edges are mutations, denoting how they are related. Okay, so back to our previous example, the augmentation variety for the right trefoil. This two-dimensional affine variety has a cluster K2 structure equipped with this quiver here, A2 quiver, two vertices, one arrow. The exchange graph, which is a data collection of all the clusters, look like the following. So let me explain what do I mean by this diagram here. So there are in the exchange graph there are 5 vertices and 5 edges. So that means this K2 cluster structure has 5 cluster clusters. And for each cluster, I need to describe for you the TARS chart, the cluster variables, and the quiver. Okay, I didn't draw the quiver because for the A2 quiver, however you mutate, it looks like the same. So it's always this quiver put at each spot. And the 2 variables written down here are the cluster variables for each cluster. And you can see that for each one of them, this is a global regular function on this variety, okay, as they're just polynomials. And finally, the TARS chart is just by setting these cluster variables to be non-zero because they give you the TARS torus coordinates. Oh, sorry. I just realized that I can't see the chats. Are there any questions in the chats?
I've been monitoring. I haven't seen any questions.
Okay, all right. Thank you.
I just have a simple question though. So is it obvious why 132 and 312 give the same filling, or
no? It's not obvious. There's there's a reason why this Lagrangian filling will produce this cluster, and it's not trivial. It's easier to compute that the underlying TARS chart corresponds to the non-vanishing locus of this one, following the theorem of Ekholm-Honda-Kalman. If you're spend the time doing the calculation, you can see that this the augmentations induced from this Lagrangian equals to this chart, but then the cluster variables and the quiver, these are non-trivial results.
I see. But if you had some like more complicated braid and you just look at all sort of permutations of ways of resolving, would there be any way to sort of know quickly from the beginning which ones might give the same, or is it really like you have to just compute?
Quick way, well, in general, no, and that's going to be one of the main theorem today, that it tells you how to determine two are the same.
I see.
Yeah, it's actually the computations is quite involved. I think it's quite involved without computer.
I see.
But this is kind of like just letting you know the answer and see how these things are corresponding. Okay, so one thing I also want to explain is that for example, from this chart to this chart, what does mutation look like? When I mutate as this z, I want to create a new cluster variable. So this is my formula: z times the new cluster variable z prime equals to 1 plus x. Okay, and then so z prime can be computed by moving z to the right-hand side. And then I use the relation in my augmentation variety to replace 1 plus x by minus z times minus xyz. And then you can compute that z prime is minus 1 minus xy here. So again, I get a new cluster variable, which is a global regular function. Okay, and then this is the exchange graph for this cluster structure. And then as Kyler just said, on the right-hand side, I just showed you like this is the final answer that how these exact Lagrangian fillings will produce each of these clusters. And you can, this sort of, tells you that these clusters can be used as invariants to distinguish exact Lagrangian fillings. Okay, so that leads to the main theorem today. So this is just a sketch, because when we have two-strand braid, this is type A is sort of better understood. When you have more strands and you allow cyclic rotations and braid moves, and then pinching in different orders, and things get really complicated. But the main theorem I want to present today is that for positive braid links, we have uniform treatment regardless how many strands you have and how long the braid is. So the main theorem has, this is a joint work with Linghui Shen and Weng. And the main properties has 3 statements. The first one is that for any positive braid, regardless how many strands you have and how long the braid is, the augmentation variety, this particular modular space that we were talking about, has a cluster K2 structure. And the rep chords are cluster variables. Okay, I'll explain what does this sentence mean here. And second, we have a way to produce for each admissible Lagrangian filling, the underlying cluster seed. Okay, and third, this is the invariant property that, given 2 exact Lagrangian fillings, if their induced cluster seeds are distinct, then these 2 are non-Hamiltonian isotopic. Here, distinct means that any property inside a cluster seed, either the torus chart or the cluster variables or the quiver, any one of those are different. These 2 are distinct cluster seeds. And then the seed itself can be used as invariant for exact Lagrangian fillings. And in particular, any data inside a seed can be used as a invariant for exact Lagrangian fillings. So let me explain, why we expect, why this cluster structure should be true. Of course, we show that, but what is the reason for that? So first of all, let's take exact Lagrangian filling. And we can think about this exact Lagrangian filling as a cobordism from the Lagrangian lambda to empty. And then because the DGA has, a definition using counting holomorphic curves in the symplectization, so as this cobordism should define for us the DGA morphism from the Chekanov-Eliashberg DGA to the trivial DGA, which is by definition an augmentation. So this heuristic can be carried out explicitly as the following. If I fix an exact Lagrangian filling together with a GL1 flat connection, a line bundle on that, this pair of data will define for me an augmentation where, its evaluation on a particular rep chord is just by counting all the holomorphic disks, and for each holomorphic disk, we count the holonomy along the boundary of the disk. So you can think about a rep chord, and then you take any holomorphic disk, which has the 1 puncture at the rep chord, and then no other punctures. And the boundary of the disk is on the Lagrangian L. And then you can evaluate the boundary of the Lagrangian using this holonomy. and then you take the sum of all of them. This gives you a number. And it can be checked that using the, I think has been done in Ekholm-Honda-Kalman, that using the curve breaking techniques, that this always defines for you an augmentation. So one thing you can do is you can keep the Lagrangian filling and change the local system on the filling, and then you ask how many local systems you can have. The answer is the character variety of the fundamental group of the Lagrangian filling. And this is just C star to the copy of the first Betti number of L. But remember the property that we mentioned before, that all exact Lagrangian fillings has the same genus. Therefore, they have the same Betti number. So each Lagrangian filling will give us a torus chart of same dimension. Okay, and another thing is that the rep chords are cluster variables. And why is that? If you look at this equation, okay, what we did is we fixed this pair L and nabla and then look at the rep chord. But you can also view this equation the other way around. If you fix a rep chord and then change your augmentation, then you can see that each rep chord will take in an augmentation and splits out a number. And this defines, because the rep chord acts on a set of all augmentations, this defines the global regular function. So they are potentially, cluster variables, and we actually prove that, all rep chords are cluster variables, and all cluster variables are polynomials of rep chords. Okay. Now
can you say why you need to assume that you're working with the closure of a positive braid to? I mean, from what you said, I didn't see how it's used.
Yeah, because if it's just this is somehow due to our limit of knowledge of arbitrary Lagrangian fillings. You can always, if you just care about the torus chart, then you don't need this. Just by the work of EHK, you can presumably, if you're capable of computing, you can just always find the torus chart. But if you want to find the cluster variables and the quiver, I don't know how to do that in general. So we're sort of limited to find those data, and but in the case of positive braids and these admissible fillings, we're able to do that.
Okay, thank you.
Okay. So thanks for the question. It's actually what I'm going to talk about next. Is that for these three data, the chart is not new. You sort of just use the EHK theory. The harder part is to find the cluster variable and the quiver. And how do we do that in general? Okay, so so our idea is to produce an algorithm. Instead of starting with one admissible filling and I name for you the quiver and the cluster variable directly, we sort of use a property that the exchange graph is connected. So we can start with any cluster, and then you sort of wander around on the exchange graph and find the cluster that you want. So the algorithm that we produce is the following. You first find an initial seed. Okay, so give me a braid. I can produce for you a quiver and a set of cluster variables. This is one cluster associated to the augmentation variety. So for example, for this braid, I write down here 1 3 1 2 1 3 1 2 1 3 1 2. The quiver look like this. Okay, it has 8 vertices. 3 are frozen, 5 are unfrozen. And then, there's a way of computing the cluster variables. There are some minors of certain matrices. I'm not going to talk about details, but you can always do this for any positive braid. You produce the initial seed. And then for each move in the admissible filling, we can we actually find an explicit sequence of mutations that produce, the corresponding cluster. So I can just describe the mutations for each type of move for you. Just a brief list, because these are sort of complicated to explain. For each saddle cobordism, each pinch move, this is actually quite complicated. It involves 2 sequences of mutations. Each braid move is a single mutation. And each cyclic rotation is 1 sequence of mutations. And you can implement all of these mutations in a calculator. It's actually my collaborator did this. It's kind of really cool. Let me show you how it works. Okay, so so here I set the number of strand to be 4, and I put a braid here. This is an arbitrary braid, and then you can just draw. Okay, so you can see the braid here. And what's written down here is the initial quiver. And what's written down here is a set of initial cluster variables. And then you can do the move any way you want. For example, you can do the braid move that's Reiter-Meister 3, for example, this. Okay. Quiver mutates, cluster variables mutates. You can do another one, for example, this. Okay, you can do the cyclic rotation like this. Okay. Because for the cyclic rotation, it's a sequence of mutations, so this quiver will change dramatically. And then I can pinch. They're also complicated. Let's see. I can do this. Oops. Uh-oh. This is, oh, sorry. It's a little bit delayed, but I just pinched this crossing. And let me pinch here. Uh-oh. Sorry, my computer is not powerful enough to do this real time. Reload. Sorry, it's every time I do this real time with Zoom, it's a little bit slow. But you can go there and try to do this. It's supposed to be fast. So you can rotate, and then you can pinch, 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 pinch. Okay. So you can see at the end you get some complicated quiver, and you get a set of cluster variables written down here. Okay. Each one of them is a polynomial of rep-cord. Okay, so I want to make a few remarks on these algorithms. First of all, as you can see, this by using the computer, we can provide an effective way of computing the TARS chart from the admissible filling. So this is actually a more hands-on method compared to the original approach by Ekholm-Honda-Kalman, because I don't need to keep track of all those holomorphic curves. Instead, I can compute the quiver and cluster variables first, and then the chart is just by setting the cluster variables to be non-zero. And another thing I want to remark is that in the theorem, there's a choice of the ground field K, because if you, I guess for the experts, that the augmentations can be defined over different fields. And what the theorem really yields is that for the purpose of distinguishing Lagrangian fillings, characteristic 2 and characteristic 0 are equally effective. Okay, it's not like we don't want to work with 0, but like for this purpose, we don't have to work with 0. Surprisingly enough, characteristic 2 suffices.
But how general is this for positive braids, or are you saying that the characteristic is irrelevant in general to distinguish exact fillings of any sort of Legendrian knots, or are you saying
for positive
that
braids
it's the
and
case
admissible? Yeah, for positive
so
braids and admissible
for positive
fillings.
braids, maybe not in general.
Not in general.
Okay.
So I guess the correct statement should be like once you have the theorem of using cluster seeds, clusters as invariant instead of just the tallest chart as invariant, and then this statement will become true. And I do want to emphasize that in this case, for the purpose of distinguishing fillings, you have to work with algebraically closed field. Okay, you take Z2 or even Z2 adjoining the homology classes, because they're not algebraically closed, they don't suffice. But once it's algebraically closed, this is as good as C, complex numbers. The third thing I want to mention is that the cluster structure on the augmentation variety we talk about here is the cluster K2 structure, whereas in some of the previous literatures, we mostly see cluster Poisson structures on modular space of sheaves. For example, in the pioneering work of Shen, D, Truman, Williams, Lasso, they look at this alternating Lagrangians and conjugate Lagrangians. See the cluster Poisson structure in the work of Shen and Weng on double Ball-Samuelson cluster Poisson, and in the paper Lagrangian weaves, also cluster Poisson. So I put a table here summarizing some of the differences. So if you come from the Floer theory and look at the augmentation variety as we did here, you get the cluster K2. Whereas for some reason, when you start with sheaves, you always get cluster Poisson structure. And the interpretation of these structures are also slightly different. For the cluster chart on the Floer theoretical side, we just think about fillings as cobordisms, and the cluster variables as interpreted as holonomy of the boundary of disks. So in our case, it's explicitly described by polynomials of rep chords. However, on the sheaf side, you sort of use microlocalization and think about sheaves that's supported on a Lagrangian brane. And in that case, you compute the cluster variables as microlocal monodromies of certain one cycles on the Lagrangian. And you often see that as a cross ratio. And these are also different because microlocal monodromies are one cycles on the surface, Lagrangian surface, whereas holonomy of the disk boundaries are the relative one cycles on the Lagrangian surface. So this is actually a little bit surprising because, I think a lot of experts know this augmentations are sheaves paper. So when we started working on this, we expected to get something similar, but instead we get a different cluster structure. So how does these cluster structures interact with this A-infinity categorical equivalence between augmentation and sheaves? Somehow that becomes a mystery at this point, and I think that's an interesting question. I don't know the answer. Okay. Next, let me say an application of what we can do using this cluster structures. It's about constructing infinite many Lagrangian fillings. So this is kind of a hot topic that question recently resolved starting from last year. So let me show you a few chronological review of what happened. So in January, in my work with Rocher-Casals, we use the sheaves and clusters and Lagrangian loops to find the first examples of Lagrangian links with infinite many Lagrangian fillings. So prior to that, we don't know the answer to this question at all. And we sort of understand all infinite type torus links, and as well as infinite many hyperbolic and satellite links. And these constructions sort of has a couple of novel recipes from the literature, and unlocks a bunch of new observations. For example, you can construct exotic Stein surfaces, which are homotopic, equivalent to a sphere, but has infinitely many closed exact Lagrangian surfaces of higher genus, which was like not known in the literature. And also new examples of non-commuting pairs of Lagrangian loops, which was now known. And we use the symmetry of the braid group to produce these Lagrangian fillings of exponential growth. It's fairly large. So kind of this unlocks this sequence of properties and constructions in contact and symplectic topology, and there are a few subsequent improvements along certain directions. The next one is in July in the paper of Rocher-Casals and Eric Zasso. They use the sheaves and the quivers and the Lagrangian weaves, and they study the fillings for such a family of braids. And in September, there's a work joined with Linghui and Daping. We use a set of augmentation varieties and the Donaldson-Thomas transformation, and to prove that for the infinite type positive braid links. And more recently, last month, there's work of Casals and Ng, where they use the DG and Lagrangian loops to produce some examples of -1 closure of positive braids. So let me explain very briefly what we do here. So the idea is sort of similar to the first breakthrough. We use Lagrangian loops. These things are loops of Lagrangian embeddings, first studied by Ekholm-Honda-Kalman. So whenever you have a Lagrangian loop, you can just graph this Lagrangian loop, and then you get an exact Lagrangian self-concordance. So the way of producing exact Lagrangian filling is, instead of try to be clever about how to pinch all of them, what you can do is you can fix a filling and then concatenate copies of this concordance. Okay, it doesn't create any genus, but it potentially give you a new exact Lagrangian filling. So you can get one, keep doing, getting more and more. So the recipe here is that for positive braids, you can look at the full cyclic rotation, which is the square of the Donaldson-Thomas transformation. And so if you have a DT transformation that's aperiodic, and then this will yield a Z worth of distinct fillings. It's a linear growth of fillings. So hopefully, if we trade off some of the extended fillings, then we can sort of do a little bit more. And there's an important property is that if the quiver is acyclic and this is acyclic and of infinite type, and then the DT is aperiodic. So of course, not all positive braid has an acyclic quiver, but you sort of use some of the idea of cobordism and some additional arguments, at the end of the day, the statement is the following: that if you have positive braid link, that's not the split union of connected sum of ADE links, and then you could have infinite many Lagrangian fillings. So this is slightly technical, but so the basic components are, if your quiver is connected, and then the standard ADE type links are following, just as stated here, for type AD and E6, E7, and E8. And when you do the split union or the connected sum, this doesn't change the quiver, just the disjoint union of their quivers. So if you have disjoint union of AD type, this is still somehow finite type. So the statement says except for all of these, and then all the rest will have infinite many Lagrangian fillings. Okay, so that's the end of my talk. Thank you.
Okay, so let's thank Honghao for the tech. So thank you very much. Are there any questions for Honghao?
I have a question.
Yes, please.
Hi, thank you for the talk. So I wanted to ask, is there a higher dimensional analog of this story where you look at local systems on exact fillings of Legendrians in higher dimension, and like are those augmentation varieties also supposed to have a cluster structure?
You mean higher dimensional Lagrangian surfaces and other higher dimension, right?
Yeah,
Or,
take any Legendrian in higher dimension and look at exact fillings in a symplectic filling of the contact manifold.
Yeah.
Is there some expectation that somehow in general dimension the augmentation variety should have a cluster structure?
Yes. So there are some preliminary examples where you can find cluster structures in higher dimension, such as Lagrangian surfaces, etc. For example, you can look at the work of Truman-Lasso on some cubic graphs, on like planar cubic graphs. But the source of the cluster structure is different from for the current setting, because in higher dimension you no longer have the Chang-Chuan's theorem that all the Lagrangian filling of the same genus, same first Betti number. So there is some cluster structure, but it comes from a different source, and I don't understand well of why there's a cluster structure there.
But why is it important that all the fillings have the same B1? I mean, it could just be that you have a variety with a stratification where, maybe some high genus fillings, high B1 fillings give you the top charts, and then like, why is it important that all the fillings have the same B1?
Oh, well, so the I guess the punchline is that there is a cluster structure for higher dimensional Lagrangian. I was just saying, like, the reason why you expect the cluster structure would be different from the setting, and I don't understand that one very well. For this one, you have cluster structure. This genus thing is kind of essential. That guarantees, that explains why these fillings will give you the charts, which are like top dimensional tori. I hope I answer your question.
Thank you.
Okay.
Sorry, I say thank you, but I
it's
muted
okay.
I was on mute. Yeah, thank you.
I had a question.
Yes, please.
You may have said this already and I missed it. In your page on Floor theory versus sheaf theory,
Yes.
you had this statement for quivers. You wrote wiring diagram equals brick diagram equals string diagram. I was curious. I'm not familiar with those terms. I was curious if you could say a few more words about them.
Sure, no problem. Let me go back to the slides. So I write these because somehow the quiver, like, you know, it give me a braid and I return to your quiver. This is just this thing itself is not new. Like it appeared in the literature in both, you know, cluster algebras and even just knot theory. Like, you know, not Lagrangian knot theory. Just in knot theory, I think Rudolph has some construction, you know, create these quivers. But for each of them, they give you the same quiver, which is like this one I produce here. It's a quiver for the initial seed. Okay, and then after that, you know, this is like, you know, this is what the string diagram or the wiring diagram mean when you draw something like that. For the braid diagram, you just replace each of this crossing by like a I, so it looks like a wall of breaks, but you know, it's the same construction at the end of the day. So it produces for you the quiver for the initial cluster, and then for all the remaining clusters, you can just mutate this quiver by quiver mutation.
Can I ask
Cool.
how you obtain the quiver for a basic example, even for the right-handed trefoil?
Yeah, okay, let me explain this. So for the rule here is that at each region, you just place a dot, and at each crossing, what you really do is you put a triangle worth of arrows. So for example, between 4, 7, 8, you put this triangle here, and then they're like the top two are half weighted and the bottom two is like weight 1. So this arrow between 4 and 7 is really the combination of the half weighted arrow for this part and then the half weighted arrow for this part. And then you do this locally for each region, and then eventually you glue up to a quiver like this. For the right trefoil, so let me go all the way back. So for the right trefoil, because you don't have like the third strand, so you don't have those triangles connecting to the top or the bottom. So it's only between these two crossings. So you put a dot here, you put a dot here, and then you put an arrow in between. That's A2 quiver.
Okay, thank you.
Yeah.
Other questions? And could you say a word about the, so I don't really know that much about these cluster K2 or cluster Poisson. What could you say a little bit about them? What the relationship is between them, or what the expectation is?
Oh, their properties are fundamentally. I shouldn't say fundamentally different. They have a lot of different traits. Like for example, for the cluster K2 structure, let me go back to the table. The cluster variables are global regular functions.
Okay.
For Poisson structure, they are almost never true. So they are still toric variables for each chart, but very likely you cannot extend them to the entire variety. This is already I didn't have a time to show you the computation, but even for the example of the A2 type cluster-Poisson variety, you can sort of see that, and their mutation formulas are different.
But is this saying that somehow with floor theory versus sheaf theory, wouldn't you expect to get the same cluster varieties using either approach, or is there a reason why you're sort of
right? So here's the thing. For example, if you take a half link, then the sheaf modular space is no longer an affine variety. It's actually a stack. So if you apply, you implement the augmentations or sheaves, you get an equivalence of categories, and then you can talk about the modular stack of objects in the aug plus category. And by their theorem, the augmentation is a stack. So in that case, the augmentation stack is not the same thing as the augmentation variety.
I see.
So it happens that for the Trifolio, it's really a special case of that, generally not true. A fact for the Trifolio is that in this case, the augmentation variety is isomorphic to the augmentation stack, which is isomorphic to the sheaf stack. It's like all the good things happens here, which you only see that for 2.3, 2.5, 2.7, and I don't know, like in general not true.
But I guess like even without going to stacks, I mean, when we say that two things are the same, implicitly we're assuming that we have a notion of isomorphism. And I mean, isomorphism of cluster algebras, it's not going to be just an isomorphism of algebras. It's going to be a little more than that, right? So I mean, it's possible that even the variety is the same. It's a variety with the same coordinate ring, but maybe two different cluster structures according to a suitable notion of isomorphism of cluster structures.
Yeah.
So maybe you have a specific one in mind, but I don't know what that is.
Yeah. Yeah, that's thanks Marco for the comment. I have been repeatedly corrected by my collaborators that the cluster variety is sort of very ambiguous thing. What you should correctly say is like you have a variety and you have some cluster structure on that variety, and this is different from having an atlas, for example, for schemes or varieties that these torus charts, they don't necessarily cover the entire thing. And that's already true even for just the half link, the T22, because there's an augmentation which is not fillable. So so the correct thing is probably like you have a variety and then you talk about cluster structures on that variety.
I think there's I think I want to mention this because I'm not sure many topologists consider that, but I think there is a student of Fomin, former student, who actually in his thesis thought about what would be a good notion of isomorphism of cluster algebras. And I think his name is Chris Fraser. So, yeah, I don't know if anybody applied his work to topology. I don't know, maybe you're able to show that in this example where you want to compare the moduli or sheaves structure and the one that you described. Maybe they're different in the sense of Fraser. I don't know. Different cluster structure.
Yeah, I don't know if Thanks Marco for the comment. I don't know if I addresses the question from Kyler or I make you more confused.
No, thanks. Yeah, that's helpful.
Okay.
Because one other thing I was wondering is, so would you expect from, in a posteriori, would you expect that these admissible fillings are somehow all exact fillings, or is it like, are there situations where you can show that there's some important fillings that couldn't possibly be admissible in the sense of cyclic moves and so on?
Mm-hmm. So for the first part, there's already a gap between decomposable fillings versus all fillings. That's, I mean, I think after EHK invented this notion of decomposable ones, no one knows there's any filling that's not decomposable but exact. I think there's a work by Cornwell, Ng, and Sivek that they constructed a filling that they don't know if it is decomposable or not. But we don't have an example of filling that's not decomposable. So that's the gap between decomposable and all fillings, and then there's a gap between admissible and decomposable ones. I wouldn't think of that question as a priority. I think it's right now the most important thing is to understand these cluster structures in some intrinsic way, and understand this table here. And once we know how to because in this table we sort of either on the first theoretical side or on the shape theoretical side, you have to put your Lagrangian in certain format to see the cluster structure. So we actually don't know the generic definition. I mean, I don't know the generic definition for these. How do you determine the quiver and cluster variables from the filling? Mm-hmm. I think once we know that, and then it's possible to address the question you just asked.
Okay, but somehow, like for the varieties that you're studying for these particular braids, like do you sort of get all? Is it possible to say that like all cluster charts appear as an admissible filling or something like that?
We don't know that yet. That's actually a hard question. Like the cluster theory abstractly gives us a lot of hints what should happen, but geometrically realize them are actually difficult.
I see. Were there any other questions for Honghao? Let's thank Honghao again, first of all. So thank you for a very nice talk. And I think, if I'm not mistaken, so I'm going to turn off the recording.